For example, the renewal process whose inter-arrival time follows IID with the uniform distribution between the interval 0 to 1, the renewal function is e power t minus 1, because inter-arrival time is uniformly distributed between the interval 0 to 1. Therefore, you know what is the fn of t, n-fold convolution of f. Substitute that is t power n divided by n factorial. After simplification, you will get e power t minus 1. That is the renewal function for a renewal process whose inter-arrival times are IID random variable with uniform distribution between the interval 0 and 1. Now we are going to relate the probability density function of inter-arrival time with the renewal density function and renewal function in Laplace form. We know that the renewal function is nothing but the summation n is equal to 1 to infinity fn of t, n-fold convolution of f, where f is the CDF of inter-arrival time. In equivalent form, using the Laplace transform, the m star of s, that is nothing but the Laplace transform of m of t, renewal function. That is nothing but summation n is equal to 1 to infinity the n-fold convolution of f in Laplace transform as a function of s. That is same as the small f of n-fold convolution in Laplace form divided by s. We know that the derivative of n-fold convolution of CDF is nothing but the n-fold convolution of the probability density function. So this can be written as 1 divided by s, summation n is equal to 1 to infinity the Laplace transform of probability density function power n. You can simplify. After that, you can find the renewal density function in Laplace, that is nothing but f of s divided by 1 minus f of s, where f of s is nothing but the probability density function in Laplace transform. From the same equation, you can get the f of s in terms of m of s also, where m of s is the renewal density function in Laplace. Now we are moving into the next concept, that is called the renewal equation. It can be shown that the renewal function m of t uniquely determine the inter-arrival time distribution f. For example, m of t is equal to lambda t corresponds to the exponential distribution break Now we are moving into the next concept called renewal equation. A renewal equation is expressed by a recursive form through an integral equation. We know that the renewal function m of t is expectation of n of t. This can be evaluated by conditioning on x1, that x1 is nothing but the time of first renewal. Hence, the renewal function m of t is equal to integration 0 to infinity expectation of n of t given x1 is equal to x, integration with respect to the CDF of inter-arrival time distribution. This integral can be evaluated by dividing into two cases. One is the case where the first renewal occurs after time t, and the other is the case where the first renewal occurs before time t. In the former case, since there are no renewals observed by time t, the conditional expectation will be 0. In the later case, the first renewals occurs before time t, and the expected number of renewals between x and t will be the renewal function m of t minus x from the definition of renewal function. Hence, the conditional expectation is one renewal already takes place before time t, therefore 1 plus the expected number of renewals between the interval x to t will be m of t minus x. Therefore, the conditional expectation is 1 plus m of t minus x. Therefore, the m of t, that conditional expectation integration, will be splitted into 2. Hence, the one integration will be 0 because the conditional expectation is 0. The other integration will be 0 to t 1 plus m of t minus x df of x. That is same as a capital F of t plus 0 to t m of t minus x df of x. So, this integral equation is called the renewal equation if m is considered as unknown, because the left hand side is the m of t, that is a renewal function. If m of t is a unknown, then m of t is written in the form of m of t is equal to f of t plus integration 0 to t. The integrand is m of t minus x. Therefore, this is called the integral equation, and this integral equation is called the renewal equation. Later, we are going to give the renewal limiting theorems as a t tends to infinity for the integral also. M of t minus x df of x can be evaluated as a t tends to infinity if certain conditions are satisfied. But here we are presenting the renewal equation where the renewal function is considered as unknown. The above equation can be written as m is equal to capital F plus m star small f, where small f is nothing but the probability density function of inter-arrival time. Now, taking a Laplace transform on both sides, you will get m star is equal to f star plus m star small f star. You can relate f star is equal to f star by s, where star is nothing denoted for Laplace form. And simplifying, we get f of s equal to s times m star divided by 1 plus s times m star, where capital M star is nothing but the renewal function in Laplace. The renewal equation can be generalized for some unknown z of t, unknown function associated with the renewal process, with the distribution function capital F as z of t is equal to q of t plus integration 0 to t z of t minus x df of x. So, the renewal function can be extended, can be generalized for any unknown function associated with the renewal process, that is z of t as q of t plus integral 0 to t z of t minus x df of x, where q of t is a known function. it can be shown that the renewal function uniquely determines the interarrival time distribution. Once you know the renewal function, you can uniquely determine the distribution function. For example, if I know the renewal function is lambda t, then you can say that the interarrival time distribution is exponential with the parameter lambda. Hence, the renewal equations are useful for deriving the quantity of interest associated with the renewal process at a function of time. So, first we discuss the renewal equation in terms of renewal function, and this can be generalized to any unknown function of time which is associated with the renewal process also. Now we are moving into the next concept, renewal times. Let x1, x2 be the time between its successive occurrence, then s0 is equal to 0 and sn plus 1 is equal to sn plus xn plus 1 defines the time of occurrence, assuming that the time origin is taken to be an instant of such occurrence. Then the sequence Sn is called the renewal process, provided the interoccurrence times are IID non-negative random variables. Then each Sn is called the renewal times. Note that the renewal process is said to be recurrent if xn is finite almost surely for every n, otherwise the renewal process is called a transient. Now we are moving into the last concept in this lecture, that is age, excess and spread. Suppose nt is a renewal process and Sn forms the renewal time. You can define age at time t of the renewal process as a of t is equal to t minus s suffix nt. The excess at time t of the renewal process is defined as y of t is equal to s of n plus s of n plus t plus 1 minus t. That is the excess at time t. Whereas the spread is the addition of age and excess, that is a spread of spread at time t of the renewal process. Here we are going to calculate what is the average excess or expectation of excess. Let yt be the excess at time t and let gt be the expectation of excess at time t. Using the renewal equation which we have discussed now, we are going to find the expectation of excess at time t. First we are making condition on x1 and the conditional expectation will be expectation of y of t given x1 is equal to x, which is greater than t, will be x minus t, while x1 is equal to x, which is less than t, then the conditional expectation will be a unknown still g of t minus x. Therefore, the g of t will be two integration. One integration is from t to infinity and the integrand is x minus t, and the second integration 0 to t and the unknown is g of t minus x. Since g of t is an unknown function of time t, this is an integral equation. One can solve the integral equation. This is nothing but the renewal equation. One can solve the renewal equation and obtain g of t. Here is the list of reference for lecture 1.